Okay, can you hear me well? Yeah, sounds sounds okay. Well, thank you for the opportunity to present the results of work package 2 to the audience in the room and online. My name is Maurice Schlichtenmeier. I'm working as a project manager for ESK, which is an engineering company with a strong focus on the underground storage of different gases, including hydrogen now. And in the HyPSTER project, I was responsible for the lead of the work package 2, which is about the modeling of hydrogen caverns and the application of methods developed so far for natural gas storage caverns to hydrogen caverns now. Okay, the objective of work package 2 was, well, one part is the validation of the suitability of existing models and methodologies derived for natural gas storage, and to see how they have to be adapted for using with hydrogen. And this is also, yeah, one of the probably one of the application of the results from the cyclic testing will be that we compare these results with the models we developed, and hopefully we can learn something from this comparison. We mainly focused on the thermodynamical and geomechanical modeling, and we also looked at methods and criteria for tightness tests. So the procedure that Grégoire has shown before for the tightness testing, we first looked at it on a theoretical basis within this work package. And once we have confirmed the suitability of the models, then we can, of course, apply them for also doing industrial scale modeling and optimizing plant design and storage design. And that was also a part that we already did carry out in this work package, and I will talk a bit more about that later on. But well, we still have to validate it on measurement data. And one important aspect is when we develop a new storage site, we definitely need this modeling before, but because no one would develop a site if he doesn't have an idea what are the properties of this storage and what to expect for this. So this is important for developing new storages. We had, carried out this work with the support of a number of partners. As I already said, ESK was leading this work package. We had contribution from Armin, Broa Consulting, Ineris, and Storengy as well. And I want to thank the project partners involved at this point already. Now, a short summary of the results is that, well, we did successfully compare two independent models, mainly thermodynamical, but also geomechanical. The tightness test method that we discussed in this work package was successfully applied. We have now a bunch of modeling data available that we can use later on for comparison with measurements. And we have sensitively evaluated several industrial scale cavern configurations, which support the assessment of storage sites throughout Europe, and finally supports the assessment of the European storage potential in salt caverns. And okay, well, the modeling tools are now available, and we have learned that for the cavern development, there is salt, the specifics of the salt on the local site are deciding, and also the distances to the brine and hydrogen infrastructure. That was also an aspect that we looked at. And we have seen that even though the distances to infrastructure are quite kind of restricting the potential, there should be sufficient potential available to serve the European hydrogen storage, the expectations for the needs for hydrogen storage for Europe. Yeah, we also had to tackle some challenges. Well, when we started with this work, there was no data available about how hydrogen storage, hydrogen cavern storage would behave. So we had to start from scratch there. We we had to think about how to transfer the tightness test methods to hydrogen storage, and how the criteria can be translated. And we had to check what is a reasonable basis to compare the different models, because they are focusing on different aspects of cavern modeling. And also, we had to ask the question: what are relevant boundary conditions to apply to the modeling, especially the industrial scale modeling, because this field is rapidly evolving, and no one really knows how a hydrogen storage will be operated in a couple of years or even decades. But I think we successfully could manage these challenges. And I now will go a bit deeper into the results. So as I said, we did a comparison of software models. We focused on the software model LOCAS from Bruar Consulting, and CavPool together with Flex3D from, CavPool is a development of ESK, and Flex3D from Itasca, it's a commercial tool. And we did a comprehensive benchmarking of these two models. On the left-hand side here, you see an example how this looked like. These are some pressure cycles. You see here the development of the cavern pressure, which is a very, very important aspect of the cavern modeling. And we found that especially for those really important parameters, we have a good agreement between the models. So we consider those both be applicable for hydrogen storages. We also found that some minor differences are, for example, regarding the temperature behavior, but these are also subject to the calibration of the models, and we hope that we can learn something about that from the measurement data, which should be available in a couple of months. And we, from this benchmarking of the models, we also had some information flow to the definition of the cycles for the cyclic tests. And we derived some ideas how this test could be designed in order to be able to learn something for the model validation. And so this cyclic test program has already been shown in the previous presentations, this was supported by our work package as well. Now, this slide shows some of the results of the EZ53 modeling. We had done some rock mechanical modeling. This was could be based on an existing calibration of the geomechanical modeling. As Grégoire has mentioned, the cavern has been leached a couple of years ago, and there are data available from earlier geomechanical tests, so could build on that. And we did some modelings of some geomechanical modelings of the cycling test, which is indicated down here. Result was that we expect a very low creep only, so it's a question whether this could be visible from the measurements. And we also did some thermodynamical modeling of this cyclic test. Here you see how the pressure curve should correspond to the volume curve of the produced brine volume. So this comparison will be done then for the measurement data as well. Okay, that's this part of the project. Well, then as I said, one important part of the project was also to apply the models that we have further developed for industrial scale modeling. So we looked how would different caverns, different cavern configurations, which are relevant for locations throughout Europe, how would they behave when they are used for hydrogen storage? On the upper right side, you see a summary of some key parameters of such cavern configurations. So we have looked at caverns in various depths between 600 meters casing shoe depth and 1,400 meters. We have looked at different sizes between 200,000 cubic meters and in this case 800,000 cubic meters. We also looked at different cavern shapes, more elongated or more compact shapes. And we also, we kind of categorized these where such caverns could be typically found throughout Europe. Well, we were interested in how these cavern configurations behave in a very long storage cycle. So, operating over multiple decades. So we applied a total of 30 years of modeling time. So at the end, we could say, okay, after 30 years of operation, how the cavern would look like, how the volume had developed, and how the temperature evolution has developed. So that was one of the parts, and we also looked at different configurations regarding the salt properties, and we decided to go for kind of medium salt properties regarding the creep behavior, which is indicated by the selection on the lower right side. This shows also the cycles, how they looked in more detail. Maybe I don't have to go into much detail regarding the cycles, but this is on the right side. You see the effect of creep closure. As expected, also for natural gas storage, cavern volumes decrease over time, and we compared a more detailed geomechanical model, which is indicated by the yellow curve in the middle, and some more simple geomechanical models, which are indicated by the blue and the gray curves on top of both. And we found that these are on the large time scale that these developments are quite similar. And so you can choose what you want to focus on and choose your model according to that. Now, we also looked at the cavern performance on the short term and how much could be extracted and injected when really going to high rates, for example. And if in the end of this comparison, we came with a comparison of the storage capacity, which is shown on the right side. And we see that we have found that all the cavern configurations we looked at, they have a very similar specific capacity when the energy content that can be stored between maximum and minimum pressure is normalized to the volume of the cavern and to the depth of the last cemented casing shoe. So of course, this number still depends on pressure limits that you apply, but well, at least in the evaluations that we did, the number that resulted from that was quite similar for all cases. And especially when you develop a new site, you would have to start with some average numbers anyway. So yeah, we could use this for the further evaluation. And as I said, we evaluated the European storage potential. This is shown on this slide. We know that there are vast salt deposits available throughout Western and Central Europe. But the question is always, how are they really usable for salt cavern storage? And we applied some restrictions regarding the geology and the properties of the salt, but we also looked how far are those deposits away from hydrogen infrastructure. We took the hydrogen backbone as something to compare with, and also from brine disposal options or brine usage options. And we came out with a reduced potential for hydrogen storage, which is theoretical but conservative. And we see that for Europe, this is still a very high amount that should be available for hydrogen storage, especially if we compare that to the storage demand. So the learning is that, well, if we are willing to develop those storage sites, at least salt should be available in the vicinity of the required infrastructure. Now, the next steps for this work package, there is not much to do left in the HyPSTER project. We have to compare with the modeling of the EZ53 with the results. But after this project, it would be useful to apply the models also to large-scale storage. And of course, if we think further for development of storage site, we know that it takes a lot of time. So we should start now. And for the development and choice of storage sites, I hope that we could prepare some tools that can support this. I invite you to check the website for the deliverables that we have prepared. This deliverable D2.9 summarizes the evaluation of the European storage potential, and the deliverable D2.6, which is still upcoming, but this will contain the comparison of modeling and measurements. Thanks. And I don't know if we have much time left for questions, especially as the coffee break is coming.
We have one online question, so maybe we'll take just one.
So Olivier is asking, you mentioned 7 tubing for performance modeling. What about 9 to 5/8 typically used in other salt caverns for UGS?
In this case, we in fact only looked at the 7-inch tubing, because it looked like the diameter wouldn't be so really restrictive in this case. But of course, as you said, other bigger dimensions are very common. We would expect that we have, could extract hydrogen at a higher rate through larger tubings. The boundary conditions applied here were the rate of pressure change. So they are not, if we fix that as a boundary condition, the hydrogen should go through the tubing anyway, and we don't come even close to things like choked flow or so. It would only affect the velocity of hydrogen in the tubing. Yeah.
Okay, thank you. We have a second question online with a really short question and answer.
Simon is asking, regarding the modeling, did you investigate removing the brine and modeling the use of a cushion gas?
We focused on modeling the in the thermodynamical modeling we focused on the gas phase, and we don't model cushion gas and working gas separately. So it's just the amount of gas in the cavern, and for the industrial scale modeling, we had the whole cavern filled with hydrogen, and for the EZ53 modeling, we focused modeling on the part on the upper part of the cavern, which is actually filled with hydrogen. I hope this answers the question.
Thank you. Thank you, Maurice.